All right, let's get started. Okay, let's see what we covered in our last lecture. In our last lecture, we finished talking about our chapter, we almost finished talking about our chapter 4, right? So which is the sources with memory. In particular, we proved the theorem of entropy rate, right? And then we talk about the hidden Markov processes, right? So yeah, this is a theorem for entropy rate, and this theorem tells you how to compute the entropy rate, right? So which is a limit when n goes infinity, and then of the conditional entropy, right? So basically, we don't need to compute the joint entropy and then normalize it, right? We only need to compute this conditional entropy here. And remember how we proved that, right? There are several steps to prove that. So if you don't remember it, just review your lecture notes. Okay, there are a few steps there. So yeah, that's kind of interesting. Yeah, and then we consider some special cases of the entropy rate, right? So one case that we consider here is the stationary Markov chain. Okay, so here are two important properties here. So first one, stationary, right? So now you should think, so what is stationary in the case of Markov chain, right? So basically means that, okay, first of all, that Markov chain has to converge, right, to a stationary distribution, right? Basically it means that it has to be, number one, irreducible, number two, aperiodic, right? And then, so in this case, we can make sure that the Markov chain will converge to a stationary distribution, right? And then, so it has to be stationary as well, right? So what is stationary? So it basically means that the distribution will not change over time, right? So it basically means that it has to start from the stationary distribution, right? So then we assume that, so the if Markov chain starting from the stationary distribution pi, then it will be stationary Markov chain, right? And then if it's stationary Markov chain, then we can use this formula to compute the entropy rate, right? So which is conditional entropy of x2 given x1, right? Because it's stationary, so it doesn't matter, right? And then, so we can just expand it, right? So this distribution is a stationary distribution, right? And this formula basically means it's the entropy of each row of the transition probability matrix, right? So hopefully all of you can recall that. So yeah, this is how we compute entropy rate for Markov chain, stationary Markov chain, okay? Okay, and then we move to talk about the function of a Markov chain, right? So we didn't talk, exactly the hidden Markov process. We consider a special case of it, right? And the special case is that, so every random variable is a function, is a deterministic function of xn. Okay, so in general, so we can consider, y could draw from a probability distribution, right? So then that will be a hidden Markov chain, hidden Markov process, right? But now we consider a special case, a simple case where every yn is a function, deterministic function of xn, okay? So in this case, the tricky part is that yn may not be a Markov chain. Okay, and we'll give an example. The fundamental reason that yn may not be a Markov chain is that, so the map between x to y can be loose information, right? Can lose information, right? So yeah, that's one fundamental reason. And but if x is stationary, then we can say that y is stationary, okay? And therefore the entropy rate exists. Now the question is how to compute the entropy rate of y, right? How we compute that? So we say, okay, of course, we can use definition to compute it, right? But we say that, okay, so if we use definition, so which is not definition, the theorem, which is given by this, right? So the drawback of that is that it's hard to know when it converges, right? Because this guy, although the difference can be very small, but it's hard to know when it converges, right? So basically, in this case, so we do want a lower bound and upper bound, right? So if the difference between the lower bound and upper bound is small, then we say it's converged, right? So basically, that's our idea. So we can characterize upper bound, which is given by this, right? And we also have a lower bound, it's given by this, okay? And then basically, we can say, okay, we have upper bound here, lower bound here. The only difference here is that we have x1 here, okay? Yeah, we can put a y1 here. It doesn't matter, right? So that will not change because y1 is a function of x1, okay? So the only difference is here. So we don't have x1 here, right? Then we can compute. Then we can show that, when n goes to infinity, the difference between the upper bound and lower bound, they are the same. I mean, the difference goes to 0, Okay, and in the book there's a proof of that, right? So it just, it's again, so this is a kind of a converged series, right? So there's some typical proof of that, similar to what we covered before, right? We show that it's monotonic increasing or monotonic decreasing and so on, and then the limit exists, and then we can manipulate to show this goes to 0. Okay, so if you want to know how exactly it is done, then just look at the book. Okay, and we finish here, right? So yeah, we finish exactly here. So in this lecture, let's continue talking about chapter 4, and then we move to chapter 5 again. Okay, so today we're still in the sources with memory, right? And then we're going to talk about the AEP for stationary ergodic processes. Okay, so and then we'll go back to it. So this still is our chapter 4, and then we'll go back to our chapter 5. So we'll continue talking about lossless. Source coding. Okay, and this is our chapter 5. And so here, in the following maybe a few lectures, so this lossless here basically means 0 error. Yeah, because we kind of covered the asymptotic 0 error already, right? Okay, great. So let's talk about AEP for sources with memory. Okay. Okay, so basically the idea is the following, right? So before, what we know is that we have an IID random process, right? And then, so we can use everything what we covered before, right? If we want to encode or do the source coding or compress this IID source, then what do? We use AEP. I mean, we use the typicality encoding, right? So that's one option. Okay, so basically we need a typicality property for this IID source, right? But now, let's say the source is not IID anymore, it's with memory. Okay, then can we still use this AEP idea? Right, before, remember, so how did we define the AEP? Yes?
It was like for an infinite signal of like length n, whereas n goes to infinity,
Mm-hmm.
and like the probability of getting a signal that has like a non-equal number of zeros and ones goes to 0.
Say again. So what goes to 0? The probability of?
The probability of having a signal that's like non-typical, or
Uh-huh.
like a different number of like ones and zeros for the length of the signal goes to 0, right?
Yeah, right. Yeah, but yeah, good. Yeah, okay. Yeah, and we have two ways to define it, right? So one way is a strong version of the typicality. So basically, we work for each probability, right? We count number of 0 and 1s, right? And then we say, okay, the number of 0 and 1s will be similar to the probability, and then, it's typical. But we have another definition, to which is the entropy typical set, right? So for those things, we only work for entropy, right? So it's something like this, right? So basically, when n goes to infinity, and then this will goes to probably the entropy, right? That's improbability. Okay, so this is what we talk about. Okay, and later on we're gonna see. Okay, so probably you'll ask why we need two kind of typical set, right? So what does the strong typical set does, right? So why we need these two definitions? Right? Anyone thought about that before? Yeah, obviously we show one is stronger than the other, right? So basically it means that the weak typical set will cover the strong typical set, right? So, and we prove that, right? But what's the advantage of having these two definitions?
I assume the convergence type or something? I mean, you're talking about this as some probabilities that they're one.
Yeah.
Stronger,
Yeah, convergence is one thing because convergence is one thing, but yeah, I don't think that's the most important thing. So what is the most important thing? No, before everything is defined in IID, right? Yeah, it's not obvious. So yeah, probably the book didn't talk about that too much. So basically, we're going to see that probably in the very end of our class, right? So the tricky part is that when we define the joint typicality, right? When we define, we have two, and not the last part, maybe in chapter 7 or so. So if we say two random variables are jointly typical, okay, so it's like x, y, we define it this way, right? In that case, so the definition of the joint typical for strong typicality is much easier than this entropy typical. Okay, I just mentioned that, but later on you're going to see why that happens. So okay, so this is basically the definition for the typical, right? This is a AEP property for the IID, right? For IID sources, right? But now the idea is that okay, so we want exactly the same thing for some stationary process. The question is, can we do the similar definition here? Can we? Yeah, the answer is definitely yes, right? You can see that. So this is defined on a sequence of axes, right? The only thing we need to make sure is that this guy converge, and that's it. Okay? So yeah, it's very straightforward. So, but in order to make this converge, right? Because now it's not IID anymore. If it's IID, we know we can break it, right? So we have a log here, right? We can break it into multiplication, and then it becomes a summation. We just use law of large numbers, and then it will converge, right? It's okay. But now we cannot do that anymore because it's not IID. What should they do? Right? That's why we say this concept kick in, right? It's called ergodic. Let's see what ergodic is. So who heard of ergodic before? Yes, who learned? Chandler is not here today. So yeah, he definitely know that. Yeah, for who take the communication class, probably we mentioned that. Okay, so yeah, let's define what is ergodic. So ergodicity is pretty much the law of large numbers for some type of stationary process, right? So we basically want the same thing there as what the law of large numbers give. Okay, so ergodic process basically means the following. Okay, so first of all, what we need is that for this sequence, so let's say n goes to infinity, and then we do a average of all the random variables. Okay, so if it's IID, so this guy will converge to its mean, right? But now it's not IID anymore, so this will converge to something that we may not know. Okay, so we assume that is with probability 1. Okay. Yeah, we don't need to worry too much about this with probability 1 in this class. But so this with probability 1 means what? So who heard of it? Yes.
So you want me to say, it's the whole almost sure.
Exactly. Right. So this means almost sure. Okay. So it doesn't mean improbability, right? So we call it almost sure or probability 1, right? Basically means that it almost happen, will happen, but something that will not happen has 0 probability, something like that, right? It's a legit event, but it will happen with 0 probability. But yeah, we don't need to worry too much about it. It just it's just the definition here. So and this mu is just a deterministic value. deterministic value. Okay. Okay, great. So yeah, this basically means it's ergodic, right? But normally we use a concept called mean ergodic. Okay, so what is mean ergodic? So we say if this xi is stationary, right? Remember what is stationary, right? The distribution does not change over time, right? So if it is stationary, then, so since the distribution does not change over time, okay, so mu will be equal to the expectation of it, right? Because xi does not change over time, so mu is just equal to expectation of xi, right? Therefore, for ergodic stationary process, so this limit will give you the mean, right? So which is exactly the same as for the IID process, right? We just, okay, so we're working on, and then, if we have this kind of definition, then, everything else will be straightforward. So basically, we have a theorem. You can see how to prove the theorem in the book, right? So don't prove that here. So basically it tells you something we just mentioned. So this is the definition for the AEP basically. So if this random process is stationary and ergodic, then we can prove that this guy, yeah, probably missed, yeah, it didn't. This guy, probability x1, x2, up to xn, right? So that will equals to, take a guess, what? What? Say it louder. Entropy. Yeah, entropy is for IID, right? So what that should be equal to? Entropy rate, right? Yeah, that equals to entropy rate. Again, so this happened with the probability 1. Okay, and this obviously, so that's the joint probability of x, right? Okay, and and for all the x, again, so we have the same definition for the AEP, right? For all the x within epsilon region to this entropy rate, then that's our AEP property, okay? So from this theorem, so we just have exactly the same definition for AEP as before, right? Nothing changed, okay, because we have this, right? We just need to replace this by entropy, right? And then we go back to our previous definition, okay? Very good. And from here, we can see that, so the AEP property holds for stationary ergodic process. Stationary ergodic okay, it holds for stationary ergodic process, okay, and then we can define the typical set in a very similar fashion, right? So then we can define the entropy typical set. So again, we call that A epsilon n, okay, as the set of sequences x in this such that the probability of this guy will roughly equals to this, right? Yeah, of course, S will be within the epsilon region, right? But roughly speaking, so all the x's that are in the typical set, so they roughly have the same probability, right? Which is given by this number. Okay, and obviously, and we can show that, so for all epsilon bigger than 0, right, then the limit of the probability that x in the typical set So that will equals to 1. Okay, so everything happened before can be seen here. Okay, so lastly is the coding theorem, right? So basically, again, we can use all the coding, the typical coding, decoding there, right? And then we can get exactly the same result, right? We just encode something in the typical set, and there we're fine, right? Okay, last thing is that, so this, the result consequences for data compression. So basically means that what we have seen for DMS holds for discrete, stationary, and ergodic process, ergodic source, right? Okay, and then we just need to replace this guy by replacing this with the entropy rate. Okay, and then everything will stay the same. Okay? Yeah. All right, so this is the typical for, it's a very small generalization for what we learned before. Okay, any questions? Okay, so no question, let's continue. So then let's talk about lossless source code. Okay, so now we start by considering, so we kind of seen this before, right? So now we consider the case where we don't have error. Okay, errorless. And then we'll go back to the case of error. Okay, so yeah, so now since we cannot allow any error, so you remember that 0 error and asymptotic error are totally different. Okay, asymptotic error means that we allow errors basically, right? Because in practice, n is never infinity, right? For any finite n, we have an arbitrarily small. We have a small error there, right? Error goes to 0 doesn't mean error is 0, right? So now we consider a 0 error basically it means that we have to code every symbol, right? So before we can ignore some symbol, right? But now we need to code every symbol. Okay, so that's the difference. Okay, therefore, so we have some new definition here. So now the problem is more complicated than before. Okay, so we see the first part. So let me introduce you some notations and the definitions. Okay, introduction. Okay, so now we need to kind of redefine the code, the source alphabet and the code alphabet. Okay, let's see how we can define those. Right, and also we need to redefine the code length. So again, we let X, this set, be a finite. Alphabet, right, and we let, okay, this xn equals to some vector x, and for each of them we have an element, right? And this for all n, and xi is in the set of x. Okay, so now we define, so x star, so this set is the union of all the sets with different n's. Okay, so that equals to the union of from 1 to n. Okay, so this should be calligraphic. Okay, so and each element in this x star, so we call that small x star. Okay, very good. And similar, we're gonna have a code alphabet like this, right? So okay, so we let L x star be the length of x star, okay? And then we now see that X is our source alphabet, and Y is our code alphabet. So this is the same as before. Okay, and we say we have a source code. We denote our source code as C, for example, right? So that is a map from X star to Y star, right? And the definition of Y star is similar to X star. It's a union of all the possible n's of yn. Okay, does that make sense? Right, so this is the definition of source code, that's it, right? We do not define what? Error probability. Okay, what is the error? What is the error probability? What is feasible, right? Because we do not allow any error in this case. Okay, so now we have a few cases to consider, right? So before, if we allow some error, right, we can just do some very simple mapping, right, and all the codes have equal lengths. Or technically, if some codes are not in the typical set, we give an error symbol E, right? Technically, it's not the same length, but you know what I mean, right? But here, so the things is more complicated, so we need to be more careful, right? So we have a few cases to do the encoding. Okay, we mentioned you one case, right? So before I say, maybe I can show you a little bit, so if you don't recall that. So when we talk about this, right, and when we think about this way, right, and we know, I mean, for this one, from here, we can see that, so this is basically kind of sequential encoding, right? It's based on what we can see in previously, and then we encode the next symbol, right? It's kind of sequential encoding, right? Remember, so this guy will be less than or equal to the entropy rate over n, right? And the entropy rate is hxn, right? So hxn is basically can be understood as a block code, right? To just take n symbols and then code them together, something like that, right? So now we have a few cases to consider given by this, right? So first of all, we consider block code. Okay, so which means that for block code, we have a few cases to consider, right? So one is that, so we can have a fixed to variable length code, okay? And we have variable to fixed length code, and a variable to variable length code, right? Which basically means that, okay, so we may code every n symbols altogether, okay? And when or we may code like one symbol, two symbol, three symbol, and a map, right? And or both the source code, both the source and the code have different lengths. Okay, we have three cases to consider, right? So basically, what we do here is that we have fixed to variable length code. Second is that we have a variable to fixed length code. Third is variable to variable length code, right? Are we cover all the cases? Is there a fixed to fixed length code? Is there or no?
Well, if we do,
right? So it's kind of silly, right? If we do fixed to fixed, then nothing happened, right? So there's no fixed to fixed, right? If it's fixed to fixed, then we know which is better, right? It's always, so there's no fixed to fixed, okay? So this is like a block code. Okay, and we have another case which is sequential. So which means that based on what we have seen before, and then we're going to code the next one, right? That is also very common, right? And from that, it looks something familiar, right? So basically, the sequential code is kind of a special case for deep learning or this foundation model case, but we focus more on block code because it's easier to analyze, okay? And we also use that in practice. Okay, let's see an example, okay? So for example, we consider, number 2, we consider the fixed to variable length code. Right, this is the most common code that used in practice. Right, and for example, let's consider our alphabet is A, B, and C. Okay, so this is our alphabet, and then we can code them individually. Right, let's say, so the length of our source is just 1. Right, we just take A, B, and C here, and we encode them individually. Right, for example, we can code A as 1, B as 01, C as 00, right? You kind of seen that before, right? You can see this is a fixed to variable length, right? So from here, well, the length of the source is 1, right, fixed, and then the length of the code is not fixed. I have 1 and 2 here, okay? All right, so, okay, so next question is that, what are the rules for the coding? What are the requirements, right? Because we need to decode it and with 0 error, right? And then we need to have some rules, right? So one rule is that the code must be uniquely decodable, right? So we don't want many-to-one mapping, right? That has to be uniquely decodable. Okay, for this kind of code, we call that singular, non-singular. Okay, the code must be non-singular. The meaning of that is as follows, right? For the code CX, so that denote the code word. Code word. Okay, so for the code word CX and the code word CX prime, so they cannot be equal if X and X prime are not equal, right? So we cannot, have many-to-one mapping, right? So it has to be not that, okay? So this is kind of obvious. Okay, so now the question is that can this guarantee the uniquely decoding? Right, would that be enough, the unique decodability? We kind of mentioned that before. Yes.
I don't think so.
Yes.
Because if the code is variable length, how do we know what we are decoding? How do we know when we've completed the code word?
Exactly. Right, that's a problem. So basically, we can see one example of that, right? So we say this, however, this cannot guarantee the unique decodability, right? So basically, yeah, what you mean is that, again, we can see this example. So we code A as 1, B as 10, C as 0. Okay, so in this case, we can see that. So this is non-singular, right? For every symbol, we have a different code, right? But there's no unique decodability here, right? The reason is that if we receive, let's say, receive 10, then can you decode? Right, you cannot, right? Because 10 means either B, right? Or A and B, right? A and C. Okay, so we don't know. If we receive 10, we have no idea what is really going on, right? So then that is not very good. Okay. Then we need to see, okay, so for what kind of code we can guarantee the decodability? Right? How can we study this problem? Yeah, exactly. Yeah, here you can see that basically you can see this 1 is a prefix of B, right? So basically means that, you know, for B, it has A, right? That's not good, right? That's great, okay? But how we can guarantee that? Right, so that is our next topic, right? So in order to see how we can study this problem systematically, so we need to introduce a few more notations, okay? And then I'll introduce you a simple code here. Okay. Definition. Okay, so now what we study is fixed to variable lengths. Okay, we'll only focus on that case. Okay, fixed to variable lengths. So now we define, so what is the decoding function in our case? Okay, and then we're going to define, so what is the average length of the code? Okay. Let's see. Okay, yeah, let's write it down. So a fixed to variable length lossless source code of block lengths n with binary output is formed by the following encoding function by so the encoding function is defined in this way. So we have f here, and so that's a map from xn to this, right? You can see that that's somehow it's a special case of what we covered before, right? So we see a source code is from x star to y star, right? But that's a general case, right? But now we have to define that from xn because the length is fixed, right? From xn to y star. Okay, again, y star here is for all n union of all yn. Okay, but now we consider y is only binary in 0, 1. Okay. And by decoding function, so g, so this is a function that we map from y star to xn, okay? And then based on f and g, such that for all x in xn, we have, so our decoding function, this guy equals to x, okay, and we denote this source code as the NFG source code C. Okay, calligraphic C. Yeah, that's the definition of fixed variable length source code, lossless source code. Okay, so now let's define what is the length of the code, right? Because now the length is variable, right? So we don't have the same length, right? Then how can we define the length of the code? Okay, so basically we define the length of the code as the average of all the code word. Okay, so yeah, that's pretty straightforward. Okay, for a given fixed to variable length lossless source code NFG. Okay, the associated length function is defined as the following. So we use LX, so this to denote the number of symbols in our encoding function, right, fx. Okay, and then the average code length is given by, so we use ln to denote the average code length. So that's equal to this, lx, lxn. So that equals to basically, we have all the code, we have all the source information here, and then we have our probability distribution, and then lx. Okay, so that's the average code length. Okay. Okay, next. So we may want to know what is the fundamental limit of this code length, right? What is achievable, right? So any guess? So what's the best code length that we can achievable? So now remember, we do not allow any error, right? Zero error, right? So we know if we allow a little bit error, so that'll be our entropy if it's an IID source, right? So, but now it's still the entropy. Yeah, let's consider IID source for simplicity. Yeah, because based on what we just discussed in the beginning, right? They're the same, right? There's no big difference. Just need to replace entropy by entropy rate, then we're fine, right? We'll just focus on IID from now on, right? So will entropy still the best thing we can achieve without allowing any errors? Yeah, the answer is yes. So we can still achieve the entropy, right? So basically, normally in information theory, zero error and the arbitrary small error, in many cases, they have the same bound, but in some cases they don't. Okay, but point-to-point is the simplest case. Normally, in the point-to-point system, we're the same, right? There's no big difference between zero error and asymptotic error. Okay. Right. So from this definition, so let's write down the theorem. So we consider a DMS system, right? So just for simplicity, right? For any epsilon bigger than 0, there exists a fixed two variable lossless source code of sufficiently large block lengths n such that, so this guy, the average code length, the average length of the code would be less than or equal to the entropy of x at some arbitrarily small number. Okay, so when n goes to infinity, so this number will go to 0, right? So basically it means that the entropy is achievable, right? Okay, so how can we prove that, right? So this theorem tells you there exists such kind of a code, right? The only thing you need to do is to construct the code. Okay, so based on what we have learned before, right? So can you construct the code?
Assign the things that happen most often, the smallest symbols.
So again, yeah, I think that's right. Yeah.
Yeah, and then things that happen very rarely, very long symbols. Right? Or long.
Repeat.
Oh, okay.
Yeah, that's correct. Yeah. Yeah. Or did everybody understand that? Oh, then you don't need. Yeah, basically, yeah, we kind of mentioned that in last or one lecture before, right? So it's a very simple idea. So basically, this is a whole set, right? And then, so this is set of AEP, the typical set, right? So before, we only encode the typical set, right? So, but now, we need to encode whatever outside. right? How can we encode whatever outside, right? So this one is ignored before, okay? But now we do not ignore, but now don't. We don't ignore that, right? So, but if we don't ignore that, we need to assign a length of a code, right? We need to assign a code there, right? How to assign a code, okay? It turns out it doesn't matter too much, right? What is the most naive way to do this? So we know, right? So this is the size. Oh, this is the size of all the code word, right? Okay, we just use this length, right? So if we take a log 2, right, and then take a ceiling here, then so that's the most number of code word needed, right? We just assign some of those to here. So this is it's the upper bound. It's definitely enough, right? So this equals to what? N log 2x, right? So this is the length of the code, right? We assign this length to all the source information here with this equal length. That be okay? Right, that's what we do, okay? Okay, great. Yeah, we need, so this is the upper bound, right? Let's say we need at most, so this number of binary symbols, 0 and 1s, okay? And then for those for those that are in the typical set, so what do we need? Yeah, we only need, do you remember? So the size of the typical set is 2 power n times h, right? So now we just need n times hx plus epsilon, this amount of bits, right? So we covered that before. So we need this number of binary symbols. Okay, very good. So here we need, so for each code word here, we need this number of bits. And for the code word here, we need this number of binary symbols, right? Are we done? As we said, right, so we need to guarantee. So this is not the prefix of this one, right? So basically, we just use a different starting point here. So we, for those code word, we prefixed by 1, and for those code word, we prefixed by 0. Okay, then we can guarantee they are totally separate. Okay, so in this case, yeah, think about that. So in this case, nobody will be a prefix of the other one. Okay, and then by doing this, so we can compute the length of the code, right? Let's just compute it, and then we're done. Okay, computation of this is relatively straightforward, right? So basically, we just use the definition here, right? Definition is given by this, px times lx, right? So this is the definition, right? So now we just need to break it into 2 parts. The first part is in the typical set. The second part is not in the typical set, right? First part is when x is in the typical set, right? And then we have this px. So in the typical set, we know the length of the code, right? So that's the ceiling of n times h plus epsilon, right? And we need plus 1 here, right? Because we have a prefix, either 0 or 1, right? We need one more bit there, one more binary symbol there, okay? And this is one thing. And the other thing is when x is not in the typical set. So in this case, we have the ceiling of n log cardinality of x, okay? And then plus 1 for the prefix, okay? Right, so next one is that we need to compute the upper bound of it, right? So the ceiling is unknown here, right? We need to remove the ceiling. How to remove it, right? Because we need the upper bound, right? So if we don't like this, we just add a 1 here, right? Don't like this, just add a 1 here, right? Then we add 2 basically instead of 1. So this constant doesn't matter, you'll see. So this will be less than or equal to. So now we can break it somehow, right? So basically, see, so everything here is the same, right? So this probably doesn't matter, right? The summation of this probability, we know that is almost 1, but it's less than, so this guy is less than or equal to 1, right? And how about this? So it's the sum of all the probability of the symbol that's not in the typical set, right? When n becomes large, so the probability of those will be very small, right? So those will be less than epsilon, less than or equal to epsilon, for example. Okay, therefore, so and then we can, so this mean we use 1 to replace it. Okay, then we have n hx plus epsilon. Yeah, we can, here it's epsilon. We can assume this epsilon are the same. We let them the same. It doesn't matter. Okay. All right, and plus, let's see, 2, right? So we have a 1 plus 1 here. Okay, so and then we add epsilon multiply n log cardinality of x plus 2. Okay. Yeah. Okay. Very good. And now we're almost there, right? So basically, now we can write everything out. This n and this n canceled. We have hx plus what? Epsilon plus 2 over n plus epsilon n log x plus 2, right? 2, I mean, there's an n, right, somewhere. Yeah, let's see. So this n will be disappear, and we'll have 2 over n, right? And now we let this guy together equals to delta epsilon. Okay, and then clearly, so, or, we let this to be less than or equal to delta epsilon, whatever, right? And then this will become 0 when epsilon goes to 0. And n goes to infinity, right? And then we're good, okay? And then we prove that. So the average length of the code is less than or equal to entropy at an arbitrarily small number, right? Any questions? Okay, then we're done. All right, so, okay, that's it for today. So we're going to continue talking about that in the next lecture. Okay, thank you.